Start today, we're going to do a true or false quiz on quadratics. You'll get 10 seconds for the first three and then it will increase as we go along. If it's true, try and show why it's true. And if it's false, state the correct answer. Here goes. You'll get 10 seconds for these first three. Question 1. Three, two, one. Question 2. 3, 2, 1. Question 3. 3, 2, 1. Whew, have a little breather. 1 to 3 done. Now you've got 20 seconds. Give you a few seconds to compose yourselves. Right, let's do this. Question 4. 3, 2, 1. Question 5. 3, 2, 1. Question 6. It's the last question on this 20-second lot. Okay, I've actually lost track of the time. Let's say 3, 2, 1. I think that was 20 seconds. Okay, last round. 30 seconds now for each of the final 4 questions. Let's do this. Three, two, one. Question 8. Vertex is another name for turning point. Three, two, one. Penultimate question. Three, two, one. And the last question. Five, four, three, two, one. Finish. Of course, you can pause the video and go back if you didn't quite have enough time. Let's go through the answers. Okay. Question 1. This is true. If the discriminant is less than 0, b squared minus 4ac is less than 0, we get no solutions. The reason being that we'll be square rooting a negative. Question 2. Could this be the graph? False. If the discriminant is equal to 0, we get 2 solutions, but they are the same. That's what we say. Sometimes people say there's one solution, but we get a repeated root essentially. So the graph will look a bit like this, or like, oh, that didn't quite touch. A bit like this. Question 3. Skipped on to different slides. Question 3. This is false. We get x plus 2 equals 0, or 2x minus 3 equals 0, and we're going to get x equals minus 2, or positive 3 over 2. You basically need to make sure you're taking the negative. False. Question 4. This one is true. You could have actually done this one by expanding the bottom one out. I guess I was hoping that you try and factorize it, just practicing that skill. One's got to be positive, one's got to be negative. We've just got to try 2 and 9, or 9 and 2, 1 and 18, or 18 and 1, and this is the one that works out. Question 5. This one is false. Did you get caught out? So b squared is going to be 25, then minus 4 times 3 times minus 1. We've got a double negative going on, so it's 25 plus 12, not 25 minus 12. We're going to get 37 as the discriminant, not 13. False. Question 6. This one is also false. So the best way to do this, especially in a time limit, is to use our method of completing the square. So we can write it as x plus 2 all squared. Let's put the 3 there for the moment, equals 7, and then divide through by that 3. Take the square root. It's going to be x plus 2 is equal to plus and minus the square root of 7 over 3. So x equals minus 2 plus or minus the square root of 7 over 3. The 2 is not being divided by the 3, so we need to modify it basically. That is how it should have been. Oh wait, that's not right either. The it's because that's not square rooted, so that's how it should have been. I know how I can see. So I'm trying to work out how you would have got that solution. If you'd left the 3 there and then square rooted it, you might have accidentally written 3x plus 2 equals plus or minus 7, and then you might have minus the 2 and then divided by the 3. I'm not sure how you would get to that easily, but anyway, the correct solution is there. This was false. Question 7. This is true. There are no real solutions. So all you need to do, well, I say all you need to do is first of all multiply 3 by 2. So 2x squared equals 3x minus 2. Rewrite it as a quadratic equal to 0. Then check b squared minus 4ac. We don't need to write down the whole formula. It's going to be 9 minus 3 all squared, 9 minus 4 times 2 times 2, and that is going to be less than 0. So you get no real solutions. True. Vertex is here. This is also true. So for this, we need to complete the square. X plus 3, remember we have that number here, squared minus 9 plus 10, which will become x plus 3 all squared plus 1. The minimum is going to be 1, and this is going to happen when this thing is equal to 0, because this thing is always greater or equal to 0. So the minimum is when it's equal to 0, and that's going to be when x plus 3 is 0, so when x is equal to minus 3. And we could sketch that with the turning point, like so. 9. This is true. At least it looks like it's true. We get the intercepts for free. The minus 1 goes here. To get where it crosses the axes, we'd need to set 4x squared minus 1 equal to 0. This would give us x squared equals a quarter. If we took the square root, we'd get plus or minus the square root of a quarter, which is plus or minus a half, which are these 2 points here. So it's true. And the last one is false. Most easily done probably by trying to substitute the numbers in. You can actually check equations by just substituting in. 0 works, -1 actually works, but 1 doesn't. We get 1 plus 2 plus 1, which is not equal to 0. So that's the one that's the problem. You might have done it instead by actually just solving it. Factorize out the common factor of x. You'll do more on cubics. We've just touched upon them. And actually this one here then factorizes to x plus 1 all squared. So what we get is a repeated root on the -1. We're going to get x equals 0 or -1. Just for fun, let's sketch it. Let's sketch y equals that graph, because it would go through -1, but it would also go through 0. So it would be coming, because it's a positive cubic, it's going to look like that. It's going to come up, touch the axis, come back down, and then go up. That's what that cubic will look like. Okay, good effort. How did you get on? Well, if you got 0 to 3, I think you need to go back and try your quadratics again. If you got 4 to 6, then you're doing okay, but keep practicing. I don't know whether it should be that or that. If you got 7 to 9, well done. Well done, actually. You even get one with a little square for his head. And if you manage to get 10, fantastic. You're looking pretty good with your quadratics. Okay, good effort. On with the rest of the lesson. Hi, today we're going to look at hidden quadratics. This equation here is not a quadratic because the highest power is 6. However, it is a hidden quadratic, and we can show that through a simple substitution. We can let t equal x cubed, because then t squared is equal to x cubed all squared, which is x to the 6. And we can rewrite this equation in terms of t, and it will become t squared minus 7t minus 8 equals 0, which is now a quadratic. How did I know to do that substitution? Well, the 3 is half of the 6. And so when we make the substitution, you can see, because we're squaring it and we're using this third rule of indices, you double 3 to the 6. And that will generally, that will be the case in general. As long as your quadratic is essentially of this form, x to the 2a plus say 3x to the a minus some constant, then it will be a hidden quadratic. Whatever so a might be it could be a fraction, it could be a nice whole number, it could be all sorts, and of course you can get numbers in front like this, but all of these will be hidden quadratics. So that's what you need to spot. All the ones today are going to be, you're then going to be able to factorize. So just be aware of that. In theory, you could get one that uses the quadratic formula, but the skill generally being tested is that can you identify that it's a hidden quadratic, and then can you solve it from there? So we can solve it from here, because this is going to factorize to t minus 8 t plus 1 equals 0. So t is equal to minus 1 or 8. We're not done, because we have to then substitute back in for our original unknown, which was x. So x cubed equals minus 1 or 8. And this is, we need to take the cube root. So the cube root of minus 1 is minus 1, because if you do minus 1 times minus 1 times minus 1, you get minus 1, or 2 in this case. That is our answer. Now, if you become, I'm just going to throw this out there right now, but if you become really confident with this, then you can actually do it a second way. You can actually just factorize directly in terms of x cubed. So it would be x cubed minus 8, x cubed plus 1 equals 0, which would give x cubed equals minus 1 or 8, and so on. It is shorter. for ones like this, it is quite a good method. For ones that get more complicated, and you'll see, it's probably best to use a substitution. So I'd say be aware of both. The substitution is a slightly safer way to go. Okay, I hope that makes sense. Let's try some more. So pause the video, try these two out now. So these are both quartics, but they are both hidden quadratics. Hopefully you can see what I'm talking about with the relationship between the x to the 4 and the x to the 2. Here are the answers. I'm going to talk through them. If you're unsure where to start, then at least let me start you off with both. So I would do a substitution t is equal to x squared in both cases, actually. Because then t squared is going to be x to the 4. We're going to get t squared minus 5t plus 6 equals 0 here. That's going to become t minus 3 and minus 2. So t equals 2 or 3. Now remember, that is equal to x squared. So get x back in there. And from that, we can take the square root, but just remember to include the plus or minus. So 4 answers here. We don't get 4 answers for this second one, so let's see why. It's going to become t squared minus 5t minus 36 equals 0. T minus 9 t plus 4 equals 0. So t is equal to minus 4 or 9. X squared equals minus 4 or 9. But because we're only dealing with real numbers in A-level maths, we actually have to reject this one. We can't square a number and get a negative. It's not possible for a real number system. So we reject this one, and that's going to leave us x squared equals 9, which hence we then square root to give us plus or minus 3. Okay, so just be careful. You don't always get, you don't get the same number of solutions every single time. Right, we're going to move on to fractional indices. You can get quadratics with fractional indices. Let's have a look at this. So if you're feeling confident, try them out. Otherwise, I'll go through the first one. Let me just start you off actually. So here, again, you can see that a half is double of a quarter. So your substitution is going to be t is equal to x to the quarter. And over here, it's going to be t is equal to x to the third. This leads to these solutions. Let's see how that comes about. Because when I do t squared, I'm going to get x to the quarter all squared. I'm going to do 2 times a quarter, I'm going to get x to the half. So it's going to become 3t squared minus 8t plus 4 equals 0. And suddenly I brought in a quadratic where the coefficient in front of the t squared is not equal to 1, but we can deal with that. If it's going to factorize, it's got to be 3t here and t here, or the other way around. So I need 2 things that are going to be negative for numbers, because I've got a plus 4, but I've got a minus 8. So I'm probably going to try minus 2 and minus 2, which does work. I'll get minus 6t and I get minus 2t. Fantastic. If you didn't spot that, you'd have to try 4 and 1 or 1 and 4, but this is going to work. So t is going to be 2/3 or 2. Remember, that is x to the quarter. So now we've got the 4th root, so we're going to need to raise the power 4 to get back to x. This one, 2 to the power 4 gives us 16. This one, when you raise 2/3 to the power 4, you can just raise the top to the power 4 and the bottom to the power 4. 2 to the power 4 is 16, 3 to the power 4 is 81. So that's where the solutions have come from. This one, very similar. T squared minus 5t plus 4 equals 0. T minus 1, t minus 4 equals 0. T actually, if you get confident, you can just then go straight to, you can just say that it's going to be x to the third equals 1 or 4. We've got the cube roots, so we're going to cube 1, we're going to cube 4 to give us these solutions. Okay, try these next to yourselves to get a little bit sneakier now. If you're unsure, I'll start you off. Well, I'll start you off with this one. So actually, this is a hidden quadratic in terms of x to the half. Let t equal x to the half, because when you then square it, you'll get back to x. And here we need to do a bit of rearranging first, so I will come back to that one. Here's your answer here. So we're going to get 2t squared minus 7t plus 3 equals 0. For this to factorize, we need a 2t and a t. It can only be, it's got to be both be minus, so it's got to be minus 1 and minus 3. It's not going to work if I put a minus 1 here. I need the minus 3 there and the minus 1 there. So t is equal to a quarter or 3. But remember, that's x to the half, or the square root of x. You've got to remember your fractional indices. You're in trouble if not. So x to the half is going to be the, sorry, I went straight to the answer then. That should have been a half. X to the half is a half, or 3. Now I square them, so I'm going to get a quarter, or 9. Brilliant. This one, this is a hidden quadratic, but it's harder to see now because we've just got the square root of t here and here. We don't have an obvious relationship like we did before. We need to create that obvious relationship by multiplying through by the square root of t. Basically, whenever you've got a fractional equation, you're trying to not like get rid of it being a fractional equation. So if we multiply through by the square root of t, we get t plus the square root of t equals 20. And I've turned it into something like this. You can, if you want, then write it as t to the 1 plus t to the half minus 20, because we always want to set it equal to 0 in this kind of factorizing scenario. And then it's much better. Now, we've actually got an equation in terms of t, but it's not yet a quadratic, so we need to do a substitution. So I'm going to use u. You can use just something else other than t, because we've already got t in the equation. I probably wouldn't use x, but you could do. U equals t to the half, because then I'm going to get u squared plus u minus 20 equals 0. So it's going to be u plus 5 and u minus 4 equals 0. And that, remember, is the square root of t. So the square root of t equals minus 5 or 4. Now be very careful before you just square these. You cannot have the square root of something equal to minus 5. This is different than if you had, say, x equals 5. X squared equals 5. You could do that x is equal to plus or minus the square root of 5. But that's different than saying the square root of x is equal to minus 5. You can't square root a number and get a negative. It's always going to be positive. This is a function and it's always positive. So actually we need to reject this. Because if you try and put minus 5 into the original, that's probably the easiest way of seeing it. You'll be taking the square root of minus 5, and that's just not, you just can't do it in the real number system. So we reject it. Instead, we're going to get 4, which you can see does work actually. Yeah, it's good. That's going to be 4 plus 1 equals 20 over 4. That does work. We need to then square it. So we're going to square it and get just the one answer. T equals 16. Hopefully you're happy with that. I think that, you can see we're stepping it up a little bit. Imagine you see this in a few months' time. You've got to play around with it, change it into this, see that it's a hidden quadratic, and make sure you reject solutions that need rejecting. 2 more to try. So here I would do a substitution. T is equal to 3x minus 2. That's what we've got, because then this is going to become t squared. Sorry, 3x minus 2 all squared. And here again we've got to kind of manipulate the fraction first before I do. Well, you could do a substitution first, but I think it's best to get rid of the fraction. Here are the two sets of answers, I should say. So here I'm going to get t squared minus 5t plus 4 equals 0. That's going to give me, actually I think we've already dealt with a hidden quadratic like this. T, that's going to give us that, maybe not. T equals 1 or 4, but that, remember, is 3x minus 2 all squared. So we're going to get this case here to start with, and I think it's best to just like deal with it one case at a time. So then 3x minus 2 is going to be plus or minus 1. So 1 or minus 1. And that's going to give, if I add 2, I'm going to get 3. I'm going to divide 3 by 3. I'm going to get my first solution, x equals 1. And here I'm going to add 2 to minus 1. That's going to give me 1. Divide by 3. I'm going to get my x equals 1 over 3. Let's deal with the second lot. So 3x minus 2 all squared equals 4. 3x minus 2 is going to be plus or minus 2. I should probably be writing ors in here, but that's what I mean. So here it's going to give me x equals 4 over 3 by adding 2 and dividing by 3. And here I'm going to get 0. Those are my 4 solutions to this problem, this nice hidden quadratic problem. You really don't want to be expanding this, to be honest. It's not going to be good. So imagine you see this in a while. Like if you start expanding it, it's just bad times, I think. Much better to have it like this and recognize it as a hidden quadratic. This final one, I'm going to multiply. Do you know what? Maybe I'll do this. I don't know. Should I do the substitution first? I'll talk about it at the end, I think, because I just think it's good to get rid of it as a fraction. I'm actually going to multiply 3 by 2x minus 1 all squared. So I'm going to get 5, and then I'm going to get 4 2x minus 1, because when I times 3 by 2x minus 1 all squared, one of those 2x minus 1s is going to cancel out with this one down here, and that's going to equal 2x minus 1 all squared. I hope that makes sense. That's a bracket. Because this is good, because now I can write it as 2x minus 1 all squared plus 4 lots of 2x minus 1 minus 5 equals 0. And I've turned it into something I can recognize as a hidden quadratic. Let t equal 2x minus 1. Again, don't start expanding it. It is in hidden quadratic form. T squared plus 4t minus 5 equals 0. T plus 5 t minus 1 equals 0. T is equal to minus 5 or 1. Now let's remember that was our 2x minus 1. So when we have minus 5, we're going to get minus 4 by adding 1. We're going to divide by 2. We're going to get minus 2. When 2x minus 1 is 1, we're going to add 1. We're going to get 2x equals 2. We're going to divide by 2, and we're going to get 1. So it does all work out. Now, I was umming and ahhing whether to do the substitution first, and I guess you could recognize that it is going to become a hidden quadratic, and you could have done the substitution right at the start. 5 over t squared minus 4 over t, because you could get a question like this anyway. I've not put one in like that, but of course that could come up. And then you can times through by t squared, and it's perhaps a little bit easier to see that's going to become 4t, and that's going to become t squared, because you can see you're going to get a t squared on the top, and that's going to cancel with that. That's what I've just done. Up to you which you do. Okay, brilliant effort. Well done. There's a load of hidden quadratics here. You can see, there's just so many different ways it can come up. We have to treat them like carefully, but essentially it has been the same technique throughout. We've just talked about little things along the way, like when you need to reject solutions and why you should never expand the brackets like this. So I hope you're feeling happy about these hidden quadratics. Thanks.